Hi everyone, in this video I'm going to explain about decrease and conquer technique. This decrease and conquer technique is another algorithm design technique just like divide and conquer technique. In divide and conquer technique what we are doing, every time the given problem of size n that we are dividing into two halves, that is n by 2 and n by 2. Every time we are dividing into half. But in this decrease and conquer technique, we are just decreasing. That means we are reducing the problem. See, out of 4 basic arithmetic operations, addition and multiplication increases the value, whereas subtraction and division decreases the value when we do that operation. So in divide and conquer technique, if the problem size is large and complex, we are dividing into two halves, n by 2, n. We are performing divide. So here in the divide and conquer technique, we don't have any freedom. Every time we need to divide the given problem into two halves, that's it. So, but in decrease and conquer, we are having complete freedom. We can reduce the problem size or we can decrease the problem size how much we want. Okay, so in decrease and conquer, how we'll do, suppose this is the problem size of n, we are reducing some smaller size. Let us take this is larger problem size n, that I am reducing into some x, I am reducing this x. Again, still this problem size is still large. Again, I'm reducing some more. Let us take this is a y problem. So like that, I'm keep reducing the problem into sub-problem into some smaller size. Once we get the solution for the smaller instance problem, from that solution, we'll exploit the solution of the overall problem. I will repeat. So in decrease and conquer technique, what we will do, the problem size is large, we will reduce into smaller instance. Okay, let us take x. Now again, this subproblem size is still large. Again, we are going to decrease this problem size into further smaller. So like that, we keep reducing, we keep decreasing the problem size into smaller instance. So once we get the solution of the smaller instance of the subproblem, from that solution we'll exploit the solution of the overall. So let us say, for example, assume I want to calculate what is the cost of 35 kg mango. Suppose I want to calculate the 35 kg mango. Assume this is a huge number. So I'll keep reducing. Let us say 25. Again I'll reduce it to 15. 5. Let us reduce 1. So now I will get this for 1 kg, how much I will find out. So now assume for 1 kg, the answer is, for example, let us say 200 rupees for 1 kg. Now I got the solution for this 1 kg, I got 200. Now from the solution of this 1 kg, I can get the solution of this 35 kg. This is how we are exploiting the solution for the overall problem from the smaller instance. So in decrease and conquer technique, we are reducing the problem size into smaller instance of the problem. Okay, once we get the solution for the smaller instance problem, from that solution, we are exploiting the solution of the overall problem. Now the question is, how much we need to reduce the problem size? Assume the problem size is 100. So in divide and conquer, it is fixed. Every time I'm dividing to half. So in divide and conquer what? The problem size is 100. I'm dividing to problem size of 50. Problem size of 50. So again, this is problem size of 25. Problem size of 25. So like that, I am dividing every time. So there is no question how much. But in decrease and conquer, how much? From 100 to 50. Or 100 to 30, 100 to 60, or 100 to 90, how much we have to reduce? That's the question. In order to reduce the problem size, okay, so there are 3 methods in the divide, decrease and conquer technique. We can reduce or we can decrease the problem size by 3 methods. So decrease by constant factor, decrease by varying factor. Let us discuss one by one. So let us discuss first decrease by constant. So in this decrease by constant, so it is fixed. Every time we need to decrease the problem size just by 1. Okay, that means every time we need to decrease the problem size by 1. Suppose for example, the problem size is say 50. Okay, next I reduce it to 49. So next again 48. Next again 47. So like it goes on. That means every time I'm reducing the problem size by 1, 1, 1, 1. Since every time we are reducing the problem size by 1, this method decrease by constant, also called as decrease by 1. Okay. So the best example for this are the problems in which we are reducing by 1. That is n factorial, computing n factorial, computing exponential a to the power of n, BFS problem, that is breadth first search, depth first search, then topological sorting, so generating permutations. So these are some of the examples which will use us this decrease by constant. That means in this every time we are reducing by 1. So let us take these 2 examples. For example, how we are using this decrease by constant in n to the power n factorial. See, in n factorial, suppose I assume I want to calculate 5 factorial. How we are calculating 5 factorial? We know that 5 into what? 4 factorial. So again, 4 factorial I don't know. So 4 factorial can be done as what? 4 into 3 factorial. So again, we don't know 3 factorial. So 3 factorial can be calculated as what? 3 into 2 factorial. Again, we don't know 2 factorial. The 2 factorial can be written as 2 into 1 factorial. But we know 1 factorial. We'll stop. So that means now I got the solution for the what? Smallest instance of the problem. So now from that solution, now we can exploit the solution for the larger instance problem either by top-down approach or by bottom-up approach. So now I got the solution for 1 factorial. 1 factorial I know 1. So 2 into 1 is 2. So that 2 is replaced by this one 2. So 3 into 2 6. So that 6 is replaced by this 3 factorial. 6 into 4 24. So that will be replaced by 4 factorial 24. 5 into 24 120. So answer is this one. So that means now we are exploited the solution from the smaller instance. So that here see 5 factorial reduce it to 4 factorial, 4 factorial reduce it to 3 factorial, 3 factorial reduce it to 2 factorial, 2 factorial reduce to 1 factorial. That means here every time you decrease by 1. Similarly, let us take for a to the power of n. So if a to the power of n is large, what we will do? That I am decreasing by 1, that is a into a to the power of n minus 1. In general, suppose assume I want to calculate a to the power of 4. I don't know a to the power of 4. Let us take, instead of a to the power of 4, let us take 5 to the power of 4. 5 to the power of 4. I don't know 5 to the power of 4. This I can write as 5 into 8, 5 into 5 cube. Both are same. But still again 5 cube I don't know. Assume this can be written as 5 into 5 square. Assume 5 square also I don't know. So that can be written as 5 into 5 to the power of 1. So now, see this 5 to the power of 1 we know 5 only. So 5 into 5 25. So in this place I can calculate 25. So 25 into 5 125. So in this place I am displaying 125. 125 into 5 is what? 625. So this is how we are going to calculate this. That means again here 5 to the power of 4 decreases to 5 to the power of 3, which is again decreases to 5 to the power of 2, 5 to the power of 1, like that. So this is how we are using decrease by constant in order to solve the problem. So summary is, in decrease by constant, every time we are reducing to the problem size by 1, 1, 1. So hence it is also called as decrease by 1. Now let us see how we can reduce the problem size by decrease by constant factor. Okay. So now we're discussing what? Second one, decrease by constant factor. So what is the disadvantage of this decrease by constant? So here decrease by constant, again we don't have any freedom. So every time we need to reduce it by only 1, 1, 1. So we saw the example, 5 factorial to 4 factorial, 4 to 3 factorial, 3 factorial to 2 factorial. Like that every time we need to reduce it by only 1. Suppose the problem size is more. Suppose say 100. So 100, 99, 98, 97, 96. So it is time consuming and it takes too many number of steps. So it is not a best method. So because every time we need to reduce it 1. So to overcome that disadvantage, we go for the next method called decrease by constant factor. Here we are having some freedom. So here By how much we need to reduce, that we can choose. That cannot be done in by what? In decrease by constant. Because here every time we need to reduce it by 1. Reduce means I need to subtract only. I have to subtract by 1 only. But in decrease by constant factor, I can subtract by 5. I can subtract by 10. That means I reduce it by 10, I reduce it by 8, I reduce by 15, or even we can reduce the problem size by performing division also. That is, I can divide by 2, or divide by 3, or divide by 8, or divide by 1 by 5th, or divide by 3 by 4. How much we want, we can reduce. But once we decided by how much we need to reduce, that will be the constant. That's why we can select the factor. But whichever the factor by which we are reducing, that factor remains the same for all the steps, subsequent steps. That is a constant. Okay. So for example, say, assume I decided every time I need to reduce it to what? 10. So now, next type, suppose the problem says, let us say 100. Okay. Problem says 100. So that next problem says what? 90. So next problem says is 80. Next 70. So like that every time I am reducing by 10, like that. So like that still we keep reducing until we get the solution for the smaller instance. Once we get the smaller solution for the smaller instance problem, from that again we are exploiting the solution of the overall problem. So this is how. Okay, now again in decrease by constant factor we can reduce by however we want. But once it is decided, it will be fixed. So now generally what we will do in this decrease and constants to have the uniformity. So in generally we are reducing the problem size always by half. Always by half means what? 50%, 50%. So that means, so here every time I am reducing into what? Size n. So next this is size of n by 2 problem size. Suppose still this subproblem size is still large, again I am reducing it by half. Okay, so that is nothing but what? Now n by 4. So assume this is what the solution we got. Assume this is a smaller instance. Once we got the solution for this smaller instance, okay, this is the solution for what? The problem of size n by 4. Now from this solution, I can get the solution for this overall problem. This is how this decrease by constant factor works. So now for example, for the example for this, again, let us take a to the power of n. Assume I want to calculate a to the power of n. Okay, so how I can use? So a to the power of n, so I will reduce into half. So that is a to the power of n by 2. Assume if I know the solution of a of n by 2, from this I can, if I make this as a whole square, I will get the solution of a to the power of n. For example, assume again I want to calculate 5 to the power of 4. So what I will do, so I will reduce it to half. That is 5 to the power of half means what? 2. So assume I get 5 square I know. 5 square is what? How much? Solution is 25. That everybody know. 5 square is 25. Now 25, if you square this solution, you will get the solution for this one. So this is how decrease. So another problem or fake coin problem, Josephus problem are some of the examples for this decrease by constant factor. So now you can ask me the question. So then what is the difference between decrease and conquer by using this constant factor and divide and conquer? In the divide and conquer also we are doing the same thing. In divide and the conquer also we are dividing into half. Then what is the difference between decrease by constant factor by half? Since in the decrease and by constant factor generally, normally we are dividing by half. This is also called as decrease by half. Okay. So then what is the difference between decrease by half and divide and conquer technique? So now let us see. So in the divide and conquer technique, so this is the problem of size n. What we are doing, we are dividing into two subproblems of size n by 2, n by 2. Suppose these two subproblems are still larger, again I am dividing into subproblems of size n by 4 into n by 4. Again this also n by 4 into n by 4. Assume these subproblems are smaller. Now what we have to do, we need to get the solution for this, and then we need to get the solution for this, solution for this, solution for this, and then I need to merge these sub-solutions to get the solution for the overall sub-problem. That means here I need to solve all the sub-problems. But here if you see, if the problem of size n, I will get n by 2, and n by 2, if it is still larger, n by 4, and I am solving only one sub-problem. After solving one sub-problem, from that solution, I will get the solution for the overall problem. That is the beauty of this one, decrease and conquer by constant factor. See here, I need to solve all these 4 sub-problems. Here I am solving only one sub-problem. So, decrease by constant factor, that is decrease and conquer technique, is much more efficient when compared to what? Divide and conquer technique. So we know how to decrease the problem by constant factor. Now what is the disadvantage of this decrease by constant? Here we don't have any freedom, always it is fixed, we need to reduce by 1. So it is a time consuming, so we go for this method. In this decrease by constant factor, we can choose by how much we want to reduce. We can reduce the problem size by doing subtraction or by division. But again, once it is fixed, again it's not possible to change. That means here we are having little bit freedom, but we don't have complete freedom. So that disadvantage we can overcome by what? Decrease by varying factor. As the name it indicates, the factor by how much we are reducing a lot. That factor we can keep changing however we want. For example, in the first step, I reduce the problem size by subtracting -5. Next time minus 10, next time divide by 2, next time divide by 4. Like that I can change by however we want. That is a complete freedom we are having in this what? Decrease by varying factor. Okay. So in decrease by factor, for example, suppose this is the problem size of n. First, next time I can divide by half. Okay. Next time I can reduce it to what? Okay, n by 2 minus 5. So next time I can reduce it to what? N by 2 minus 5 minus 10. Next time I can reduce it to what? N by 2 minus 5 minus 10 minus 2. Let's see. First time I reduce it to half. Next, that one I minus 5. Subtract by, again reduce the problem by 5. Next time again reduce by 10. Like that I can do however we want. So the complete freedom we are having in the what? Decrease by varying factor. Okay. Let us see the one best example for this. So that is what? The Euclid's algorithm to find the what? GCD. Euclid's algorithm to find. Assume I want to find out the GCD of 120 by say 45, for example. Okay. So now these are the two numbers. Now I want to find the GCD of two numbers. One is the m and n. Here what we'll do in the Euclid's algorithm, the given m and the given n. Now we'll check. So given m value and n value. M and n value are what? M value is in this example 120. This is 45. So now what I will do, I will check n value 0. If n value is not 0, I am dividing the m by n and taking the remainder. Okay, if n value is not 0, if n value is 0, we will stop dividing. Okay, now n value is 0 now? No. What I will do, divide the m by n and take the remainder. So 45, 3s are how much? Oh, 120. So 2, 90. So that means 90 means how much you got? 35. So 35 will be the what? Remainder. Okay, next. Now after doing that, what we will do? We will move n value to what? M and remainder value to what? N. So after that, what I got is, this is 45, this is 35. So now again you check. N value becomes 0? No. So divide m by n and take the remainder. Remainder is how much? 10. So now again what we have to do? So we need to move n value to m and remainder to what? N value. So now I got here 35 and here 10. Now again n value 0 na? No. Divide 35 by 10. Take the remainder. Remainder is 5. So now again what we have to do? Move this value to n. So this value to the n. So now I got this is 10, this is 5. N value 0 na? No. Divide the 10 by 5. 5 2s are 10. Remainder is what? 0. So now again you move this value to m and you move this remainder to what? N. So I got this is 5 and this is 0. When n value becomes 0, I stop. At that time, whatever the value of m is there, this will be your GCD. Okay, so here how it is decreased by varying factor. See, first time I divide by what? Divide by 45. Second time I divided by 35. Next step I divide by what? 10. Next time I divide by 5. See, like that every step I keep on varying the factor by which I am reducing the sign. Okay, this is the example for decrease by varying factor. Another example is interpolation search we can use. or inserting or deleting or searching in a binary search tree are some of the example for what decrease by varying factor. Okay, so hope you people understood. Thank you. Hope you understood the concept. If you have any questions, please write in the comments. Thanks for watching.